This article open access. The state-of-the-art in multilayer network visualization. F. McGee. M. Ghoniem. G. Melançon. V. Otjacques. B. Pinaud. First published March 28, 2019. https://doi.org/101111/cgf.13610. Citations 76. About. Sections. Abstract. Modeling relationship between entities in real-world systems with a simple graph is a standard approach. However, reality is better embraced as several interdependent subsystems or layers. Recently, the concept of a multi-layer network model has emerged from the field of complex systems. This model can be applied to a wide range of real-world datasets. Examples of multi-layer networks can be found in the domains of life sciences, sociology, digital humanities, and more. Within the domain of graph visualization, there are many systems which visualize data sets having many characteristics of multilayer graphs. This report provides a state-of-the-art and a structured analysis of contemporary multilayer network visualization, not only for researchers in visualization, but also for those who aim to visualize multilayer networks in the domain of complex systems, as well as those developing systems across application domains. We have explored the visualization literature to survey visualization techniques suitable for multilayer graph visualization, as well as tools, tasks, and analytic techniques from within application domains. This report also identifies the outstanding challenges for multilayer graph visualization and suggests future research directions for addressing them. 1. Introduction. Simple graphs are often used to model relationships between entities in real-world systems. This approach may, however, be an oversimplification of a much more complex reality better embraced as several interdependent subsystems or layers, which motivated the development of the complex networks field, GBSH 12, KB15. The concept of a multilayer network, KB*14, builds on and encompasses many existing network definitions across many fields, some of which are much older, e.g. from the domain of sociology, Moore 53, version 79, VS 85. As an introductory illustrative example, consider a person's social networks. People frequently use more than one social network platform, e.g. Facebook for their personal social network or LinkedIn for their professional. Offline, real-life, social networks could also be considered, again with relations being either personal or professional. These networks can be considered independent. However, they can also be considered as layers in a multi-layer graph. The networks overlap as some people may be present across layers. In this case, layers are characterized by relationship type, either online/offline and personal/professional. A significant change in one network may implicitly correlate with or cause changes in another. For example, a change of employer will cause changes in both offline and online professional networks, but in a different manner for each, and may cause slower, more gradual changes in the personal offline/online social networks. To answer some questions, it may be necessary to also include employers or companies as entities of the network. This makes it possible to model explicitly person-company relationships, as well as person and company relationships. In this case, layers may be characterized by entity type, either person or company. Other definitions of layers are also possible as illustrated in section 2. Examples of multilayer networks can be found in the domains of biology, the so-called omics layers, epidemiology, WX12, SMSB12, PSC-VMV15, sociology, in a broad sense, including fields such as criminology, for instance, BS85, LP99, GB07, FPSG10, GKL*13, CMF*14, BJRM15, DMR16A, Digital Humanities, MDG 16, DCHRL *12, ESCO 16, Civil Infrastructure, SIEGE-GZ *13, DUC 17, DER 17, and more. Multilayer networks have been explicitly recognized as promising for biological analysis, GMD *18. We give more details in section 2.4. In the area of network visualization, many systems visualize data sets having many characteristics of multilayer networks, albeit under a different title. Multi-label, multi-edge, multi-relational, multiplex, RMM 15, SIEGE-GZ *13, heterogeneous, DCHRL *12, SGB *14, multimodal, GKL *13, HS09, multiple edge set networks, CMF *14, interdependent networks, GBSH12, interconnected networks, SMSB12, and networks of networks, KPB15, are among the many names given to various types of data that are encapsulated by the multilayer networks definition of Kivala et al. CAB *14. Recently, initial steps have been made towards consolidating the work on visualization of multilayer networks from domains outside of the information visualization field, see MUXVIS, DEED PA15, from the domain of complex systems, or from the domain of social networks, DMR 16V, based on the complex systems paper of Rossi and Magnani, RM 15. However, to date, there has been no survey quantifying and consolidating the state-of-the-art of visualization of multilayer networks, both within the field of information visualization and across application domains. The goal of this survey is to reconcile the many visualization approaches from the information visualization field and the application domains and group them together as a consistent set of techniques to support the increasing demand for the visualization of multilayer networks. The final contribution of this work consists in identifying the key challenges outstanding in the field and providing a roadmap for future research developments on the topic. This report is structured as follows. Section 2 presents the defining concepts underlying multilayer graph models and points out the main differences they have with other related network models. The rest of the section briefly describes the application domains in which multilayer graphs are encountered. The description of the methodology followed is presented in Section 3, followed in Section 4 by the survey itself. It provides a structured account of relevant tasks, visualization, and interaction techniques pertaining to multilayer network analysis. In Section 5, we reflect on the state-of-the-art in multilayer network visualization and point out open challenges and opportunities that lie ahead of the information visualization research community. We finish this paper in Section 6 with concluding remarks and a roadmap for future contributions to the topic of multilayer networks visualization. 2 multilayer networks and related concepts. The notion of many relationships between individuals, often called multiplex relationships, is seminal in sociology, and one could argue that it already was present in the sociograms introduced by Moreno, Moore 53. The notion is central in the work of Burt and Schott, BS 85, where the challenge is to somehow simplify multiplex relationships, consolidate and substitute them for relationships involving a smaller number of relation types to ease the analysis of the network. More recently, the concept of a multilayer network has emerged from the complex networks area, a subdomain of the field of complex systems, and is a fertile ground for novel visualization research. 2.1 Defining concepts. It is important to emphasize that layers do not reduce to some operational apparatus. The concept goes far beyond a simple intent to capture data heterogeneity. While it is true, this notion is most of the time embodied as nodes and edges of a network being of different types. Its roots lie deeply in sociology, BS 85, LP 99, GB 07. This notion is used to form questions and hypotheses, where layers can be considered as innermost, intermediate, or outer, Lin 08. For instance, Dunbar et al. DCP-15, consider networks similar to our introductory example and examine to what extent online and offline layers in personal networks overlap. While innermost and outermost layers are well-established notions in sociology, the modeler is free to be creative when deciding what constitutes a layer, Dixit Kivala et al. Cab *14. That is, the notion of a layer in a network emerges from and belongs to the domain under investigation. Consequently, when discussing the notion of layer, it is important to distinguish the sociological network from the mathematical network used to describe it. The mathematical network, a graph, is but an artifact through which we may hope to observe and ultimately characterize a phenomenon occurring on the sociological network. The definition of a layer is thus a characteristic of the multilayer system as a whole, defined either by a physical reality or the system being modeled. The notion of a layer naturally occurs when describing tasks performed by analysts. It can be mobilized to form exploration or browsing strategies. See section 4.1. Formal definition. A standard graph is often described by a tuple where V defines a set of vertices and E defines a set of edges, vertex pairs, such that. An intuitive definition of a multilayer network first consists in specifying which layers nodes belong to. Because we allow a node to be part of some layers and not to others, we may consider multilayer graph nodes as pairs where L is the set of considered layers. Edges then connect pairs. An edge is often said to be intra- or interlayer depending on whether or. Going back to the example where people use different social network platforms, we would have where Facebook friends, LinkedIn connections, real-life family, friends, acquaintances, etc. 2.2 Aspects. Kivala et al. Also define what they call aspects as a way to characterize a set of elementary layers relating to some concepts. An example would be Aspect L1 capturing interaction between people in the context of their participation to events, e.g. conferences, ADH *12, with L1 for interaction during Infovis, L2 for interaction during Eurovis, etc. Aspect L2 capturing co-authorship around themes, an example we borrow from Renaust et al. RMM 15, with for co-authorship associated with some keyword. Aspect L3 capturing project partnership, with layers associated with specific programs, for example, GKL *13. And so forth. Aspects can also be used as an artifact to deal with time or geographical position. They can be captured by extending the previous definition, as proposed Kivala et al. Given any number d of aspects, a multilayer network corresponds to a quadruple, where each aspect is a set of elementary layers and, that is, while nodes do not necessarily appear on all elementary layers, they necessarily appear on at least one layer of each aspect. The set of edges of M simply is, see Figure 1. Figure 1. Open in Figure Viewer PowerPoint. Aspects can be seen as groups of layers of different types. Nodes do not necessarily appear on all layers, but they necessarily appear on at least one layer of each aspect. Kivala et al. Chose the term carefully to avoid using a term that may be unclear depending on the reader's domain. While the term dimension, in its literal meaning, may lend itself to the concept of defining a characteristic, aspect has been chosen due to the use of the term dimension as jargon in different domains. Another example lies in the domain of biology, described further in section 2.4. One aspect is the type of data, such as genomic, metabolomic, or proteomic. Another aspect might be the species or different biological pathways, as illustrated in Figure 2. If the biological data contains time information, that may also be considered an aspect. While multiple aspects are a possibility for multilayer network datasets, it is not a requirement. A multilayer dataset may be defined by a single aspect which categorizes multiple layers. See Table 1 for a sample list of aspects and layers extracted from the literature surveyed as part of this report. Kivala et al. KB *14 provide further examples in their extensive list of multiplex datasets and their associated layers. Figure 2. Open in Figure Viewer PowerPoint. a purely illustrative example of multilayer data in the context of biology. The layer can be described by the type of data as a first aspect, genomic, proteomic, or metabolomic, and biological pathway being represented as second aspect. Table 1. Examples of aspects and layers extracted from papers covered by this survey. Aspect description. Layer definition. Source paper. Source paper domain. Social entity type. People, societies/organizations. RMM 15. Information visualization. Social relationship type. Friendship, aggression. CMF *14. Social networks. Word relationship. Hyponym, homonym. HD 12. Information visualization. Year of publication. 1974. 2004. HD 12. Information visualization. Infrastructure connection type. Air connection, train connection. HMV 14. Physics. Transport mode. Air, rail, ferry, coach. GB 15. Scientific data, transportation. Omics entity type. Gene, protein, protein structure. PS *08. Biology. Historical correspondences. Letter, letter sender, letter receiver, cited book. VV 17. Historical network research. Building layout. Arrangement of house spaces. SLP *17. Robot control algorithms. Incidentally, Weymouth et al. WFC 16 propose an alternative definition they call multi-aspect graphs, where they formally define what can be considered as an aspect. Unsurprisingly, they also form a network where nodes are defined using Cartesian products collecting multiple values into a single entity. The authors describe multi-aspect graphs as forming a generalization of Kivala et al.'s multilayer network. Reconciling these different approaches is beyond the scope of this paper. Well-developed examples are certainly needed to uncover the full applicative potential of multi-aspect graphs. 2.3 Related graph models. Below, we review related graph models. See also Figure 3 and their differences or resemblances to multilayer networks. Figure 3. Open in Figure Viewer PowerPoint. Illustrative examples of related graph models, each of the 3 node types, indicated by color, of the n-partite graph could define a layer within a multilayer network. In this case, all edges would be between layers. For a multivariate graph, node attributes could be used to divide the network into layers. Defining layers by node type in this example would result in 3 layers, although that may not make sense for the system being modeled, as there would be no edges within the layers of nodes of types B and C. For a dynamic graph characterized by time slices, each time slice can be intuitively understood as a layer. Further insight could be gained by the use of an additional aspect to define layers. 2.3.1 N-partite graphs. Recall that a bipartite graph is made up of 2 disjoint sets of vertices, so that no 2 vertices belonging to the same set are connected. Bipartite graphs can be considered as a case of multilayer networks with 2 layers and only interlayer edges. The 2-mode, i.e. node type, nature of bipartite graphs result in analytics that are different to those of single-mode graphs, B97. Bipartite graph concepts are sometimes extended into n-partite graphs, as seen in our example in Figure 3a, although, in practice, many of the TW mode restrictions associated with bipartite graph are not fully retained. In practice, systems which model bipartite cases and extensions of bipartite cases, such as the multimodal networks of Ghoniem et al., GKL *13, and the academic network analyzed by Scher et al., SLT *14, can be considered instances of multilayer networks. In this case, the authors also make use of bipartite analytics, e.g. adapted centrality metrics, to better understand their network structure. Bipartite networks can be reduced to single-mode networks via projection on a mode. Such an operation may also be used to define a layer in a multi-layer network if the projection results in a layer that reflects the reality of the system being modeled. 2.3.2 Multivariate graphs. Multivariate graphs, KPW14, are those in which nodes or edges carry attributes or properties, as described by Schreiber et al. SKB*14, there is a relationship between multivariate graphs and multilayer graphs. Some variables or attributes in a multivariate data set often serve the purpose of distinguishing nodes and edges that belong to different layers, e.g., the type of social network platform in our initial example. There are also multivariate visualization applications such as that of Pretorius and Van Wyck, PW08, which define their graph as having discrete sets, which can be considered analogous to defining layers. However, in the majority of cases, research into multivariate visualization lacks the a priori definition of a layer defined by a physical or conceptual reality related to the system being modeled. In faceted datasets, multivariate data items are grouped in multiple orthogonal categories. Originally used as an approach to search and browse large data stores and text corpora, SCM*06, CSL*10, later work extended the faceted approach to include relationship visualization. LSR*09, ZCCP13. Datasets can have many different facets such as spatial and temporal frames of reference, or multiple values per data item, and as such can be considered multifaceted. Visualizations for multifaceted data are those which show more than one of these facets simultaneously, see Hadlack et al. HSS 15 for a survey of multifaceted graph visualization techniques. Hadlack et al. Discuss primarily 4 common facets of network structure considered in network visualization and their composition, partitions, attributes, time, and space. These facets may be considered to be very similar to instances of Kivala et al. S aspects. However, they can be considered as different ways of exploring a single data set, which is unsurprising given the origins of a faceted visualization. The techniques described are still very useful for developing approaches for visualizing layers, particularly where the layer type matches the Hadlack et al. S selected faceted categories. However, faceted network visualization approaches do not meet all the needs for multilayer network visualization. While multilayer networks may use notions similar to these facets to characterize layers, multilayer network visualization also focuses on the interactions between layers and the role of layers in the network as a whole. 2.3.3 Dynamic graphs. Dynamic graphs are graphs whose structure, nodes and edges, and/or associated attributes may change over time. Analysts are often interested in comparing the state of the network at different points in time. Within the domain of complex networks, Bacaletti et al. BBC*14 consider the dynamics of multilayer networks, and in many cases, time slices of a dynamic or temporal network are simply mapped to layers. The notion of dynamic networks is also mentioned by Kivala et al., who note that they can be considered as a type of multilayer network. A set of dynamic time slices can be considered layers in an aspect representing time. As multilayer networks can have multiple aspects, a temporal aspect might be just one of many. In their report on dynamic network visualization, Moody et al. MMBD05 explain the importance of multiplicity in social networks, i.e., the overlap of types of relations. In particular, they point out that linking relational timing to tie types allows better investigation of social dynamics. A recent survey of dynamics graph visualization techniques was provided by Beck et al. BBDW17, but does not consider layers in any context other than a hierarchical graph. 2.4 Application domains and data. Across all of the application domains mentioned in Section 1, advances in sensors, scientific equipment, and technology mean that researchers have access to more data than ever. This wealth of complex data is often best understood as a multi-layer network model. 2.4.1 Life sciences. Within biological network visualization, there are many contexts in which a multilayer network approach may be beneficial, GMD*18. Biologists have access to more genomic, proteomic, and metabolomic data, allowing for the construction of complex multilayer models of intricate biological processes. Interactions taking place within the genomic, proteomic, and metabolomic levels can be modeled as individual networks, but interactions also occur between elements sitting in different omics levels within a larger biological system, where the aspect characterizing the layer is the node type, CWV*10. This corresponds to the strongly rising topic of systems/integrative biology, where the challenge consists in understanding the interplay and the cascade of effects taking place at the different levels of the biological system at hand. GB*10, KET13. A prominent task for biologists analyzing biological pathways consists in comparing a species-specific pathway to a reference pathway, MMF17. In this specific case, species type can be considered a defining aspect for a layer. Another task is to compare tissue-specific interaction networks to understand why certain tissues, e.g. plant root tissues, synthesize certain molecules which are not found in other plant tissues. In this case, tissue type is the defining aspect for a layer. 2.4.2 Social Sciences. Data sets within social network analysis frequently contain multiple types of edges to support examining the different types of relationships between people, e.g. more recently, CMF*14, but also in much earlier work such as VS85, LP99, or multiple types or modes of nodes, e.g. modeling a citation network containing researchers, institutions, and publications, GKL*13. Within social sciences, there are also contexts in which many networks may be compared to one another. For example, examining social networks produced as a result of cell phone activity, as done by Frary et al. FPSG10. The contemporary use of multiple online social networks provides a vast amount of data. This allows for complex social multilayer networks to be built, which may help sociologists gain deeper insight, RMV14. Other fields such as food microbiology have adopted social network analysis techniques and applied them to understand problems such as the spread of disease. This can be seen in the work of Crabbe et al. CD*17 to understand the spread of salmonella in a large poultry farming enterprise. Different networks are generated based on contact between different types of entities. From a multilayer perspective, contact between entities can be considered an aspect, with the entity types defining the different layers. 2.4.3 Digital Humanities. Within digital humanities fields such as digital cultural heritage, archaeology, and data journalism, many multilayer approaches, VV17, MDG16, DHRL*12, ESCO16, RRV*18, MEVL*17 can be found. Digital access to source texts and natural language processing techniques such as named entity recognition and topic modeling allow for vast digital humanities data sets to be built, MDG16. Co-occurrence relationships between people names, locations, organizations, as well as other entities form a typical multilayer network whose analysis may reveal insightful interaction patterns. 2.4.4 Infrastructure. Modern vehicles often provide a wealth of information about modern transportation networks. These networks can also be modeled as multilayer networks. For example, Halu et al. HMB14 model the air and rail transportation networks of India as layers in a multilayer network. A paper by Galati and Barthélemy, GB15, is another nice example. The Internet and associated infrastructure provide vast amounts of data about themselves and can be modeled as multilayer networks, as done by Rees et al. RAB*14, who represent the power grid and the Internet as separate interdependent layers in a multilayer infrastructure network. Recent work concerning urban infrastructure systems highlights the necessity to adopt an integrated approach to urban planning, taking into account the interplay between multiple networks such as transportation networks, energy networks, telecommunication networks, and water/wastewater networks, DER 17. Some of the related objectives may be to reduce the cascading of failures across these networks. BPP*10, but also to develop an efficient repair strategy to restore services after disaster, SDH16. The precise representation of buildings to support robot control algorithms is a related domain as seen in SLP*17. In this work, the graph represents a layout of the floors of the building with their interconnections. A layer is a floor containing rooms. An edge represents a direct connection between two rooms. Interlayer connections modeled connections between floors. This kind of model reduces the amount of data to be analyzed by a robot. The vast number of instances of complex data sets produced across all these domains demands a visual approach to help understand it, and that approach will often be multi-layer network visualization. 2.5 Complexity and human performance. Multilayer networks are implicitly more complex than standard networks, which is not surprising given their origins in the domain of complex systems. The complexity can be increased by the type of task, the sheer volume of data, or the density of its connectivity. Within information visualization, there have been many studies completed examining the impact of these various types of complexity on human performance at specific tasks. For example, Ghoniem et al. GFC 05 examined the impact of edge density on choice of visualization approach. See section 4.3.3. The notion of practical densities for empirical evaluation is one which prompts much discussion. Mel 06. While graph size has been recognized as an important factor for quite some time, there is no widely accepted definition of what is a large or small graph. VLKS*11. With many empirical evaluations running pilot studies or basing their chosen size of large graph on assumptions rather than a standardized definition. While we do report on the state of empirical evaluations with respect to multi-layer networks, see section. For point 6, the topic of human performance and network complexity is a vast topic in and of itself. Therefore, a full analysis is beyond the scope of this state-of-the-art report on multi-layer networks. For a detailed survey on network complexity and empirical evaluations, the reader is referred to the work of Ghoniem et al. YAD*18. 3 Methodology followed. This section is about the structure of the survey, which is built on a categorization of the important features of multi-layer network and how we selected papers cited in the many domains we cover. 3.1 Categorization. The categorization of the most important features of multi-layer network visualization that are to be considered for each paper is built in a manner consistent with Munzner's Nested Visualization Design Process Model, MUN 09. Tasks and Analysis. Multi-layer systems that address new problems and domains may expose tasks that do not fit in existing task taxonomies, such as LPP*06, PPS 14. New analytics have been developed for multi-layer networks, and new visualizations have been developed as a result, e.g., DEED-PA 15. Data definition. This aspect of the review looks at the nomenclature used for the data set, e.g. multiplex, heterogeneous, which aspects are used to define layers across the data, as well as the structure of the data. Visualization approach. We analyze and categorize the various visualization approaches described, identifying novel approaches and novel applications of existing approaches, e.g., BISB 16. While many visualization systems described in this survey were not explicitly identified in the original source as being for multi-layer networks, we point out ways in which they may be applicable and targeted to them. Interaction approach. Interaction with multiple layers will often be more complex and requires innovative techniques such as HD12, SLT*14, RMM15. Attribute visualization. Multilayer networks can also carry multivariate data, SKB*14, DHRL*12. Under this category, we will examine the impact of multilayer structure on attribute visualization. Empirical evaluation. Empirical evaluation is a challenge for information visualization, PLA 04. Within the domain, there are many guides to evaluation such as PER12. However, techniques developed in application domains may not have been exposed to the same level of rigor as those developed within the visualization domain. It is important to understand which novel techniques have been empirically validated with respect to their usability. 3.2 Paper selection. The wide range of application domains makes performing a complete survey highly challenging. Within the domain of visualization, we queried prominent journals and conferences for a list of keywords related to multilayer networks. Our main search engines were IEEE Explore and the ACM Digital Library. The list included the terms and variants of the terms using hyphens: multilayer, multilevel, faceted, multirelational, multimodal, multiplex, heterogeneous, and multidimensional. The ambiguity of some of these terms meant that some completely unrelated papers were returned. These were removed from the list based on their abstract. The prominent visualization venues included IEEE TIVCG and implicitly VAST and InfoVis, CHI, including SIGCHI and TOCHI, Computer Graphics Forum, and implicitly Eurovis, Advanced Visual Interfaces, PacificVis, Graph Drawing and Network Visualization, formerly Graph Drawing, and the Journal Information Visualization. Due to the wide range of application domains and numerous publication venues in each, it was not feasible to perform such a formalized search within them. We used our initial list of visualization papers as a seed, adding papers from the application domains which were cited by or cited them as found using Google Scholar Search. Additional papers were also added to the list of those reviewed based on feedback from reviewers of the STAR if they indicated that the papers would be valuable additions. Each paper was reviewed by at least one co-author, and the review shared with all other authors using a wiki. Papers were summarized based on the characteristics described in Section 3.1. Reviews of the paper were discussed at group meetings between the co-authors to provide a final decision on which papers should be included or excluded. All final text describing the papers within this work was validated by all co-authors. As stated in Section 1, the goal of this survey is to reconcile the many visualization approaches from the information visualization field and the application domains. Many techniques have been extracted from papers which may not have focused explicitly on multilayer techniques, perhaps using one of the names described in Section 1, e.g. heterogeneous. However, the techniques are included as we believe that they are of interest to researchers who wish to visualize multilayer networks. As part of the review process, some papers were considered, based upon the keyword search described above. However, they were omitted from the final state-of-the-art report due to their content not being related enough to the visualization of multilayer networks. For survey of multilayer graph visualizations. In this section, we begin by defining and illustrating a task taxonomy for multilayer graphs. Consistent with Munzner's model, we survey various data definitions on which the visualizations presented hereafter are built, as well as relevant interaction techniques. The survey encompasses the visualization of attributes in the context of multilayer networks and closes with considerations about visualization evaluation. For Point 1 tasks and analysis. Numerous literature surveys LPP*06, APS 13, PPS 14, KKC 15, BBDW 17 list tasks relevant to the visual analysis of different types of networks, general, evolving, multivariate, etc., and tasks have been proposed on a domain-specific basis, e.g. MMF 17. Lee et al. LPP*06 provide a general graph task taxonomy. At its top level, it considers topology-based tasks, attribute-based tasks, browsing tasks, and overview tasks. It explicitly specifies that the high-level tasks of comparison of graphs and identifying graph change over time are not covered by the taxonomy. Pretorius et al. PPS 14 focus on multivariate network. While Pretorius et al. Do consider graph change as part of their multivariate tasks taxonomy, the taxonomies of Karcher et al., KKC 15, and On et al., APS 13 both focus specifically on dynamic networks, also known as evolving or temporal networks. At the highest level, On et al.'s taxonomy focuses on three groupings: entities, properties, and temporal features. The temporal features are grouped as individual events, the shape of change, and the rate of change. These are considered from the individual entity level to the entire network level, and for both structural and domain properties. Karcher et al.'s taxonomy builds on the non-network specific taxonomy of Andrienko and Andrienko AA06 by extending it to include network data. It considers both elementary and synoptic tasks. As defined by Andrienko and Andrienko, elementary tasks involve individual items and characteristics. Synoptic involve sets of items considered as an entity, but further divides synoptic tasks into three categories. These are tasks considering graph subsets, tasks considering temporal subsets, and tasks considering both graph and temporal subsets. The taxonomy differs from On et al.'s in that it focuses more on the tasks that data items take part in rather than the data items themselves, and considers a more general concept of pattern changes that captures relational changes in the network, as well as considering tasks which provide context for graph evolution. Evolution. Murray et al. MMF 17 propose a taxonomy in the context of biological pathway visualization that contains tasks concerning comparison, attribute analysis, and annotation that relate to multilayer networks. Although most task taxonomies that have been developed so far do not directly address multilayer networks per se, they could be further adapted or extended to target multilayer network visualization. Existing literature does mention specific tasks that may be relevant for multilayer network visualizations, which we cover in this section. Some tasks may involve the temporal dimension as well, such as tracking the evolution of nodes or edges at different moments. Unsurprisingly, tasks that are specific to multilayer networks revolve around the notion of a layer. Tasks often boil down to manipulating elements within one layer or across several layers, or manipulate the layers themselves. These manipulations often lead to lower-level tasks, which are also critical for visual analytics tasks, identifying actor roles, grasping group interaction or communication patterns in social networks, etc. In the survey work of Pretorius et al., PPS 14, a task is schematized as a process. Select entity, select property, perform analytic activity. We see here an important difference with the process of performing a task on a multilayer network involving layers. Conceptually speaking, layers are genuine building blocks of a multilayer network. They are neither a simple, network nor a mere property of a node or edge. They are a conceptual construct that fully enters the analytic process when performing a task involving the multilayer nature of the network. We report here on different approaches or systems that support tasks relevant to multilayer networks. In many cases, authors have not explicitly expressed tasks in terms of layers, but rather referring to properties of the data they consider. This is the case for authors considering tasks related to group comparison or reconfiguration, HD12, CLLT 15. To this end, in anticipation of Section 5.1, We propose task categories specific to multilayer networks. We target tasks directly involving visualization, as opposed to tasks that can be addressed through computational means only. Task Category A, cross-layer entity connectivity, e.g. interlayer path. Tasks in this category aim at exploring and/or inspecting connectivity involving paths traversing multiple layers. Understanding how shortest paths expand across layers, inspecting what nodes do occur on these paths are typical examples of tasks in this category. Being able to explore cross-layer connectivity has been identified as an important user task in GKL*13. Associative browsing in refinery, KRD*15, is a good illustration of cross-layer connectivity task. It performs cross-layer random walks and collects nodes from different layers in a single view. The leapfrogging operation in DetAngler, RMM15, is another good illustration of cross-layer connectivity building a dual view reflecting how/what layers get involved when hopping from node to node. See section 4.4. Task Category B, cross-layer entity comparison. Tasks in this category aim at comparing entities, typically nodes, across different layers. This requires the ability to query entities across layers. The task may concern the same set of nodes over several layers, or distinct nodes that are somehow linked across different layers. Jigsaw SGL08 typically supports this task by allowing users to identify entities, persons, places, etc. through several documents seen as layers in a multi-layer document network. Facet Atlas, CSL*10, multi-facet query box is another good example. Task Category C, layer manipulation, reconfiguration, split, merge, clone, project. Tasks in this category aim at manipulating the layer structure itself. Such manipulation may allow for previously unseen relationships and structure to be revealed, and allow for new perspectives on the underlying data. Combining layers through drag and drop operations, as in the work of Haskowit and Dragicevic, HD12, is a perfect illustration of this type of task. Another example is G minor, CLLT15, which allows to create, edit, or refine the grouping of elements. Task Category D1, layer comparison based on numerical attributes. Tasks in this category support comparing layers to one another based on numerical measures summarizing layer content and structure. Typically, layers could be compared by looking at how node degree distributions compare layer-wise. Onto this, SMER06, where layers map to node type, supports layer comparison tasks using a metric they call interlayer node disparity. Pretorius et al., PVW08, propose a quite elaborate approach and system to perform multi-attribute-based layer comparison. Task Category D2, layer comparison based on topological connectivity patterns. Tasks in this category support comparing layers through non-numerical but rather topological features of layers, e.g. group structure. A layer could be hierarchical, inheritance, while another could show a strong scale-free structure, for instance. The work by Velo et al., VBAW15, is a typical technique allowing to compare group structure across layers. Tasks R5 and R12 in GraphDice, BCD*10, are another good illustration of such tasks. In the biological domain, the tool NetAligner, PCA12, compares different biological networks, which can be considered analogous to layers, and visualizes them in a single visualization to allow a user to determine how well the networks are aligned, i.e. overlapping in terms of nodes and edges. Table 2 summarizes task categories supported by a selection of systems and techniques cited and described in this report. Table 2. A selection of techniques/systems grouped as far as possible by task categories relevant to multi-layer networks that they either implicitly or explicitly support. Notes in parentheses refer to task labeling/naming as indicated by authors in their paper. D. Layer comparison. A. Cross-layer. B. Cross-layer. C. Layer man-up. D1. D2. Connectivity. Entity comparison. reconfiguration, numerical, topological, Vislink CC07. Multilayer graph edge bundling, BISB 16. MuxViz DDPA 15. BICoverlapper SDQ 08. Refinery KRD *15. Associate browsing. Multimodal social networks GKL *13. Q1BC, Q1A, Q2C. Hybrid Vis LWIZ 17. Q4, Q1, Q2, Q3. Det Angler RMM 15. Leapfrogging. GraphDrail DHRL *12. ManyNets FPeace G10. GraphDice BCD *10. Multifacet query. R5, R12. Hierarchical edge bundling, AVW08. Facet Atlas, CSL *10. Network Analyst Tool, XGH15. Donatian, HD12. Dynamic Communities, VBAW15. Hive Plots, KBJM11. G minor, CLLT15. Onto Vis, SMER06. Pivot Graphs, What 06? Roll Up. Circos, KSB *09. Jigsaw, SGL08. Disparity. For point 2 data definition. This subsection looks at the various data definitions found in the visualization literature on which visual representations of networks with multilayer characteristics are built. Only a few approaches explicitly mention the use of multilayer networks, both as data underlying the visualization and as a visual encoding. Most systems dealing with multivariate networks couple relational data with node and edge attributes, SMER06, WUD06, BCD *10, HP14, often using table-based representations, KS14. HP14, they do not consider any data or attributes specifying a layer structure. Chow et al. CSL *10. Consider classes of entities they call facet, which appear to naturally map to layers of nodes. See section 2.3.2. Among all, the work of Pretorius et al. PW08 is a notable exception as it introduces the notion of layers without using the term and explicitly defines nodes as Cartesian products of attributes. See section 2.1. Other systems and approaches infer multilayer structure by aggregating data from multiple sources, whether databases, case W14, or a collection of ego networks, as in DCP15, and or personal data, HTA *15. Interestingly enough, some systems do not directly target the visualization of multilayer networks, but use multiplex and or hypergraph representations to build query graphs or summarize query responses, TS13, SW13. Obviously, MuxViz DDPA15 relies on the exact definition and implementation, see section 2.1, introduced by KB *14. Which is also the case of authors mentioning explicit use of the MuxViz framework, GB15. Elementary layers originating from aspects of the network, such as time or node/edge type, are quite similar to the facets described in HSS15. Det Angler RMM15 relies on an explicit encoding of layers, with a goal to allow an easy exploration of interlayer correlation, see section 4.1. Making a distinction between layers as being either structural or functional, or of any other type, may be useful depending on the pursued goal, ATSN 17. For point 3 visualization approaches. From a multilayer network perspective, previous work in network visualization techniques may be classified based on their awareness of the notion of a layer. When this is the case, layers are visually encoded using any appropriate Gestalt principle in a way that structures the spatial representation. They are also manipulated as visual objects in their own right as detailed in section 4.1. This is why the section is organized based on the type of visual encoding used to show layers explicitly. This survey also documents and reflects on the widespread use of weaker visual cues, in the sense of McKinley's ranking of perceptual tasks, MAC 86, to encode layer information such as node or link color. For 0.3.1 one-dimensional representations of layers. Existing visualization techniques use a large variety of one-dimensional, 1D, representations of layers. See Figure 4 for examples of basic 1D visualization. This type of visual encoding relies on the law of continuation of Gestalt theory, such that the eye may perceive paths on which nodes are arranged whether these paths are actually drawn or not. This applies to circular paths, as well as straight axes or any curve shape. Figure 4. Open in Figure Viewer PowerPoint. A simple illustrative example of a vertical axis-based one-dimensional layout and a circular layout. In both cases, it is the ordering of the nodes that is more important than coordinate position. Circular representations. This body of work includes concentric circles, where each circle stands for a layer. Concentric circles are used in BSH 13, where the focus is on depicting paths through the whole set of layers, task category A in our taxonomy. Node order optimization and edge bundling are used to reduce edge clutter. A similar layout is used in the ring view of MuxViz, DPA 15, but focuses on visual correlation analysis of node attributes across different layers, task category D1. Node color encodes attribute values, see section 4.5 and figure 16, while ring order and ring thickness encode computed layer level metrics. Similarly, Circo's KSB*09 is a popular tool for comparative analysis of genomic data, where each ring/layer may stand for a biological sample. To compare node attribute values across samples, a histogram is wrapped around each ring, task category D1. Chord diagrams display layers as arcs composing one overall circle. They are used in the Network Analyst tool, XGH15, to analyze gene expression data. Links between layers are drawn as splines connecting identical nodes occurring in different layers/arcs, task category B. The analyst may click on a pair of arcs to highlight their common nodes and the bridging links. A similar approach is followed in AMH 13, CMF *14. In the presence of multilevel categorical attributes, as in HE 16, each arc of the chord diagram can further be split hierarchically, task category C. The chords would then connect nodes at the leaf level across all layers where they are repeated. Axis-based node link representations. In this category, a layer is materialized by a straight 1D axis. Obviously, the representation of a multilayer network lays out nodes on several such parallel axes. An important way of distinguishing axis-based visualizations relates to the type of variable represented by the axis, whether it is quantitative, e.g. a graph metric like node degree or any numeric node attribute, or ordinal/ranking based. Despite the visual similarity to the parallel coordinates plot ID 90, a polyline represents a path between nodes sitting in different layers/axes, rather than a thread linking attribute values across different columns in a given table entry. Kernversanen et al., CMF *14. Describe a view that uses such parallel axis arrangement and alternatively chord diagrams. An example of analyses they run consists in comparing the aggression network among students in 4 different schools based on student race group. They show that smaller groups do not show internal aggression patterns, while larger groups victimize everybody equally within the same group and in other groups. In this case, the analyst is more interested by topological considerations at the group level and structural differences between layers, task category. D2. Ghoniem et al., GKL *13, provided an approach called parallel node link bands, PNLBs. Nodes are positioned uniformly across spaced parallel axes, which represent layers defined by the node type, or mode, see Figure 5. Edges are only drawn between adjacent layers, and within layer, edges are shown in a separate visualization. Node order on axes can be set based on edge attributes or connectivity to other layers. They use their approach to analyze the National Science Foundation, NSF, funding dataset. Examples of tasks they carry out include determining whether some NSF program managers award funding to some principal investigators, PIs, more often than others on a three-layer networking containing program managers, projects, and PIs. This is an instance of task category A where the focus is on paths traversing all layers. Figure 5. Open in Figure Viewer PowerPoint. The parallel node link bands, P&LBs, representation of GKL*13. Each axis is a distinct set of vertices. Edges are only displayed between adjacent axes. Some axes show a quantitative value, e.g. project budget, while others display text strings, sorted based on a graph metric or alphabetically. The list view of Jigsaw SGL08 provides an overview of entities grouped by type, with edges being drawn between connected entities in adjacent lists. One of the main utilities of this system is to relate different types of named entities, people, geographic locations, and organizations mentioned in the same documents. Entities which are connected to a currently selected item are highlighted by color across all lists. It therefore emphasizes the analysis of paths across all available layers, task category A. The list view is complemented by a node link and a matrix-like scatter plot view, among others. Hive plots, KBJM11, differ from the previous techniques in that they arrange the axes radially. Originally introduced for the analysis of genomic data, they have been used in other domains like performance tuning in distributed computing, EW12, and in the domain of health, White EL*16, as can be seen in Figure 6. In KBJM11, node, gene, subsets are placed on separate axes based on a node partitioning algorithm. The fundamental questions they answer using hive plots include determining differences in connectivity patterns between layers, task category D1. An element's position along its axis is often calculated based on a graph metric, e.g. node degree in EW12, and may be based on the raw or normalized value of an attribute. Edges are displayed between adjacent axes only. Yet, visual clutter may still occur with real application data. Layer duplication, as in Figure 6, is convenient when the relationship to a non-adjacent axis becomes necessary, task category C. Figure 6. Open in Figure Viewer PowerPoint. The hive plot representation of health data by White EL*16, showing 4 layers/axes, toxicity type, duplicated, material, and particle size. Edges are only displayed between adjacent axes. The vertices on the horizontal axis are colored based on their cluster membership. For 0.3.22D, 2.5D, and 3D node link representations. Across the various papers we surveyed, node link layouts cropped up frequently. As illustrated in Figure 7, for the standard two-dimensional 2D layout, X and Y coordinates are assigned for each node. For the 2.5D approach, sets of nodes are assigned to planes at a different depth, and for the three-dimensional 3D approach, the nodes are usually assigned a different individual depth, Z-coordinate. The MuxViz toolkit, DPA15, from the domain of complex systems, utilizes several variants of node link visualizations. They are also used in other domains that depend on complex systems theory, GB15, BBB*16, DD17. Figure 7. Open in Figure Viewer PowerPoint. A simple illustrative example of 2D, 2.5D, and 3D visualizations of a network. The 2D layout, left, is a standard node link layout where nodes are positioned with X and Y coordinates and, usually, an orthogonal projection is used to render the visualization. The 2.5D approach, center, draws sets of nodes on 2D planes at different depths. For the 3D example, right, nodes are at different depths in that they actually have an individual z-coordinate, depth value, for position. In this example, the nodes themselves are 3D objects, spheres, rather than circles, and are shaded to clarify their 3D shape. 3D network visualizations are usually rendered with a 3D projection. As can be seen from this figure, depth is difficult to convey in a static 2D image. 3D visualizations usually require some level of camera movement to reveal occluded data, as well as the depth aspect to be conveyed through motion and/or stereoscopy. A widespread visual design consists in encoding layer information using node color or shape, as depicted in MMVD05, FHK*09, KSW14, ZB16. Color coding of edges is also used in DUC17, DDPA15. This design choice relies on the law of similarity of Gestalt theory, color similarity in this case. This design is often adopted when the multivariate nature of the network is the driving motivation of the visual design. For instance, Figure 8 represents flows of maritime traffic, using color to encode different modes of shipping or layers. The analyst looks among other things at structural changes over time, where different layers encode different time slices, task category D2. But if the analyst is interested in analyzing a given time slice, different layers may represent different shipping modes. The related task consists of comparing structural differences among the different modes. In similar visual designs, layer information is diffuse. Relationships between layers and within the same layer are mixed, and users seldom get a handle on layers to manipulate them directly. Nodes belonging to different layers are intertwined in the 2D plane when standard node link layouts are used, and edge clutter is problematic. Layer-related tasks may therefore be difficult to carry out under these circumstances. Figure 8. Open in Figure Viewer PowerPoint. A multi-layer network visualization describing the flow of maritime traffic. Nodes represent ports, and different edge colors represent different modes of shipping, taken from DUC17. While not explicitly designed with multi-layer network visualization in mind, constraint-based layouts offer the possibility to constrain a 2D node link layout in such a way that respects the concept of layers. For example, the Setcola constraint-based layout of Hoffs-Well et al. HDH18 allows users to apply layout constraints to sets of nodes, which might easily correspond to layers. Such a layout approach supports analyzing cross-layer connectivity, task category A, as well as layer comparison, task category D2. The examples covered by the authors include a food web networks and a network modeling a biological cell, and both of these datasets can be considered to have multi-layer characteristics. The multilevel layout approach of TopLayout, AMA07, is also not designed with multi-layer networks in mind, but as an approach, may be of interest in the multi-layer case. TopLayout is a feature-based approach that decomposes and graph into a hierarchy of features, hence, being considered a multilevel algorithm, and chooses a suitable algorithm to lay out each feature. Within a multi-layer network, the structure of each layer may be very different, requiring an approach that can adapt to the different features in each. The highest level feature detected by the TopLayout algorithm is a connected component. Therefore, the algorithm could be adapted to consider each layer as a connected component, but also would need to be enhanced further to consider the impact of interlayer connectivity. Inspired by the multilevel nature of some problem areas, e.g. biological networks, the 2.5D approach materializes layers as 2D translucent parallel planes in a 3D layout, similar in spirit to Figure 2. This visual design relies on the law of uniform connectedness of Gestalt theory. It separates links lying within layer from those between layers, providing a more natural support for path-related tasks, task categories A and B, than traditional 2D node link layouts. But 3D navigation is required to allow the user to change his perspective on the data and resolve visual occlusion problems. As opposed to 1D axis-based representations, the parallel 2D planes provide space to lay out interlayer links. In the 2.5D category, some approaches use color redundantly to encode layer information as in FHK*09. Other visual design options for 2.5D consist in using color to encode an attribute value or a computed metric, e.g. community assignment, by a community detection algorithm as in DDPA15. Across the different layers, from the biological domain, the Arena 3D application visualizes biological data using an interactive 3D layout, where layers are also projected onto planes and entities are connected across layers by edges rendered as 3D tubes. The authors demonstrate its effectiveness by analyzing the relationship across layers based on proteins and genes associated with a specific disease, task category A. The use of 3D layouts is much less common in the information visualization research community. While some work has shown that there may be some benefit to 3D layouts, this is only under stereoscopic viewing conditions, WM08. Outside of stereoscopic viewing conditions, there are no empirical studies which demonstrate usability gains from a 3D graph visualization, GPK12. A more widely accepted approach in information visualization, especially for the purpose of comparative analysis of graphs, consists in using small multiple views. This is often used for graph matching tasks, where the focus is on understanding commonalities and differences between a set of related networks, HD12. In the context of this paper, the networks that need to be matched are distinct layers in a larger multi-layer network, task categories D1 and D2. Whether in a 2.5D setting or in a flat small multiples setting, one challenge consists in ensuring that duplicate nodes are laid out consistently across layers by introducing constrained layout strategies as in FHK*09, HD12 to better support cross-layer entity comparison, task category B. Node link layouts have been used to compare networks visually, as done by Andrews et al. AWW09 and D. Giacomo et al. DGDLP09, but in many situations, other approaches may be more suitable. See sections 4.3.3 and 4.3.5. More generally, coordinated multiple views are often used in the domain of information visualization and in many applications, e.g. the analysis of microarray data, SDQ08. In this case, 2D node link views may be used as one of multiple complementary visualizations of a multi-layer network, e.g. KRD*15, GKL*13, SGL08. It is yet possible to eschew the idea of using a node link visualization altogether, for example, using aggregate views of nodes based on attribute data, such as a bar chart enhanced with arcs, DCHRL*12. Coordination between views is common, e.g. brushing and linking. The Dead Angler RMM15 application builds on this by also harmonizing layouts between views. It supports several task categories identified in the survey, namely cross-layer connectivity, task category A, layer manipulation, task category C, and layer comparison, task categories D1 and D2. Edge visualization. The complex structure of multi-layer graphs makes edge visualization an important challenge. It may be important in some cases to distinguish between interlayer and intralayer links. In other cases, the number of layers may cause enough clutter with respect to edges that a visualization becomes less understandable. In some cases, the chosen solution is to simply not draw all edges and to allow the user to choose which edges to see via interaction to ease interlayer comparisons, task category B. For example, the P&LB's technique, GKL*13, only draws interlayer edges between nodes on parallel axes, and intralayer edges are displayed in a separate visualization. The well-established technique of edge bundling, Hole 06, has been adapted for the multi-layer use case by Borky et al. BISB 16. The authors bundle all edges in a single visualization in an aesthetically pleasing manner, with edges being kept adjacent to each other when they share a common path and edge crossing being avoided. See figure. 9. This approach is useful for showing edges from multiple layers in a single visualization where there is no division of nodes between layers. The approach is agnostic to the source or target layer, or whether the edges are between or within layer. Task categories A and B. Figure 9. Open in Figure Viewer PowerPoint. The multi-layer edge bundling of BSB 16. Within their list-based view, Kronover-Sannon et al. CMF *14 use edge bundling between different list columns as a clutter reduction technique clarifies similarities between different edge types. The authors essentially group edges based on relation type by clustering the vertices and altering the clustering based on vertex mode. They also use a modified edge bundling in their circular layout, which distinguishes within mode edges and between mode edges. See Figure 10. Figure 10. Open in Figure Viewer PowerPoint. Edge bundling as utilized by CMF *14. Within category edges are routed around the exterior of the circle. Between category edges are routed via the interior of the circle and bundled. Quite naturally, the visualization of edge group structures, as surveyed by Velo et al. VBW 17 presents a lot of similarities with multi-layer network visualization, and some work cited, e.g. Det Angler, can be easily adapted especially for cross-layer connectivity and layer reconfiguration. Task categories A and C. For 0.3.3 matrix-based visualizations. Standard node link representations of graphs give equal importance to nodes and links and aim usually to convey structural properties of the graph at hand. They may, however, be difficult to read due to edge clutter for moderate-sized graphs and for the more complex networks encountered in many real usage scenarios. When dealing with large and/or dense graphs, matrix-based representations were found to be more readable than node link diagrams GFC05 for many tasks, except pathfinding. They have also been shown to outperform node link visualizations for some tasks concerning clusters of nodes, OJK18. Matrix-based visualizations consist of laying out nodes as the rows and columns of a two-way table. A link between two nodes is often represented as a rectangle at the intersection of the associated row and column, as illustrated in Figure 11. This avoids altogether the edge clutter problem of standard node link representations. Color is often used to encode the weight of the links when link attribute values are available. This makes matrices very similar, if not identical in essence, to heat map views frequently used in biology and other domains. WF09. Other visual designs include using circles at the intersection of rows and columns with size and color encoding link attribute values, as in CMH12. Matrix representations have been used to visualize homogeneous graphs, nodes of one type, e.g. in software engineering, VH03 and bipartite or two-mode graphs, e.g. in software performance tuning, GCFJ05. In the latter work by Ghoniem et al., the analysts needed to compare the graph structure and edge weight distribution before/after a software revision by contrasting the corresponding matrix representations, and also to monitor the runtime behavior of the software through the animation of the matrix representation as the graph structure and edge weights changed over time. Figure 11. Open in Figure Viewer PowerPoint. A simple illustrative example of a matrix visualization and the corresponding node link visualization. The ability to detect link patterns in a matrix view is conditioned by the use of an appropriate ordering of rows and columns. Various seriation algorithms, Che02, Li10, Fec15, reorder the rows and columns of the matrix to create dense rectangular blocks of links. Community detection in a bipartite graph consists in finding groups of nodes in one layer which are densely connected to groups of nodes found in the second layer, task category A. Two-way hierarchical clustering is commonly used with biological data for this purpose. The BIC overlapper system, STQ08, uses biclustering methods to find such relationships between groups of genes and related groups of medical conditions. On the visual side, BIC overlapper uses coordinated multiple views, one of which employs convex hulls within a standard node-link representation to materialize groups of genes, akin to the notion of elementary layers described in section 4.2. The overlapping convex hulls are meant to support the identification of commonalities and differences between layers, task categories, B and D2. In the presence of multiple layers, the comparison of link patterns between many pairs of layers may be useful to the analyst, task category A. Laying out small multiples of matrix views side by side is one approach. Liu and Shin LS15 investigate several possible juxtaposition strategies and assess their usability with multifaceted, time-varying networks. MuxViz DPA15 uses matrices to summarize layer-level statistics as a means to convey a notion of layer similarity to the analyst, task categories A, B, D1, and D2. In an evaluation by Alper et al., BCHAR*13, which focused specifically on weighted graphs in the context of brain connectivity analysis, matrix visualizations were shown to perform better for comparison tasks than node-link visualizations. For 0.3.4 hybrid approaches, recent work has been exploring the integration of multiple visualization techniques in an effort to better grasp underlying data, JE12, see Figure 12 for an illustrative example. Although matrices have been shown superior to node-link diagrams for dense networks, the latter may facilitate the tracking of edge directions. In this spirit, NodeTricks HFEM07 mixes node-link views with matrix-based visualizations to support typically locally dense social networks. While NodeTricks is not explicitly a multi-layer network visualization technique, it is the first hybrid approach that focused specifically on network visualization. Since its inception, the idea has been extended by other techniques to support other types of data, such as compound graphs, RMF12. Although they do not always focus on visualizing multi-layer networks, such approaches could also be directly reused or adapted to support multi-layer networks. This link, CC07. For instance, allows visualizing a data set using multiple representations at once, also explicitly displaying the cross-view links. Using the technique, one layer could be used for each representation, and interlayer links could be highlighted, task category. A. Adopting another perspective, Hybrid VIS LWIZ17 allows using the same kind of representation, but for different levels of details or hierarchical scales. In this case, a node-link view may include some levels that are shown as expanded and other levels are shown as collapsed, task category C. With additional views, histograms, parallel coordinates, more details on level attributes can also be obtained, task categories D1 and D2. Figure 12. Open in Figure Viewer PowerPoint. A simple illustrative example of a hybrid approach, mixing both matrix and node link in a single visualization. For 0.3.5 structural summary visualizations. For some graph comparison tasks, where detailed inspection of local structure is not required and only an overview is necessary, a summary approach, not showing individual nodes or edges, can be taken. In the graph thumbnail representation, YDK*18, a graph is decomposed hierarchically using what the authors refer to as a K-core component clustering, or KC3, decomposition. In this decomposition, in which the top two layers of the hierarchy are defined by the single and biconnected components of the graph, respectively, the third level consists of 3 cores within a biconnected component, and the subsequent levels are defined by K-cores, where the hierarchical decomposition is visualized using a hierarchy of circles, positioned using a circle packing algorithm and adorned with further node and edge distribution information, as seen in Figure 13. This type of visualization reveals structural information about a network, allowing for rapid comparison of networks and can be easily applied to the comparison of layers in a multi-layer network, supporting task category. D2. Figure 13. Open in Figure Viewer PowerPoint. Graph thumbnails generated to compare the structure of two graphs generated in the analysis of protein interaction networks taken from YDK*18. The color and size of the circles represent structural information in a hierarchical decomposition of the graphs. Other existing systems also provide the ability to view graph structure information as a form of summary visualization. ManyNet's FPSG10 is an approach that uses simple attribute-based visualizations, such as bar charts and histograms, as a means of summarizing and comparing networks, as seen in Figure 14. The simple charts show metrics that describe the structure of the graph. The set of charts describing a network is referred to as a network fingerprint, and the tabular presentation allows for easy comparison and sorting across networks or layers, depending on the nomenclature chosen. The annular visualization of MuxViz, DPA15, also allows for comparison of structure across layers, see section 4.5. In general, structural visualizations are used to compare graphs, and hence can be used to compare layers. Task categories D1 and D2. For a complete taxonomy of visual comparison in information visualization, see the work of Gleicher et al., GW*11. Figure 14. Open in Figure Viewer PowerPoint. The list view of the ManyNets application, FPSG10, summarizing attributes of networks using bar charts. The vertical bar charts show the distribution of attribute values, and the green and red stacked horizontal bar is a combined score based on several inputs. For point 4 interaction approaches. The discussion about user interactions may be grounded in E et al.'s categorization of interaction techniques, YAX07. According to Haskowit and Dragicevic, HD12, multilayer network visualizations may support user interaction at the level of individual network elements, e.g. individual nodes and links, and at the level of whole layers, whether single layers or groups of layers, task category C. They argue that layer-level interactions require a visual affordance, NOR 13. In particular, their system, called Donatian, supports the E et al.'s reconfigure and explore interactions. For point 4.1 node-level and link-level interactions. Traditional interactions include selection, point-and-click selection, lasso selection of nodes. Filtering, keeping/removing nodes or links based on attribute values. Navigation, to visually inspect a fragment of the visual representation using zoom and pan, or context plus detail techniques, e.g. fisheye distortion or magic lenses. These have obviously been used widely with standard node-link representations and are directly applicable one layer at a time in the context of multilayer networks. The Det-Angler approach, RMM15, combines two distinct synchronized visual representations. A first panel, Figure 15, left, displays the overall network connectivity through a node-link view between nodes of all layers. Another panel, right, displays a node-link view showing how layers interact, where interaction is measured and inferred in an ad hoc, domain-dependent manner. Det-Angler supports a leapfrogging interaction. The selection of nodes in the left panel automatically triggers the corresponding layers in the right panel, task category A. Leapfrogging, executed by double-clicking the selection lasso, expands the original selection to include all nodes, Boolean or involved in any one of the layers that were selected, or restricts the original selection to nodes involved in all layers that were selected from the layer view, Boolean and Figure 15. Open in Figure Viewer PowerPoint. A screenshot from Det-Angler, RMM15, showing how nodes, left panel, relate to layers, right panel. Selecting layers, lasso, trigger the selection of nodes they involve, red nodes, left panel. For point 4.2 layer-level interactions. Interacting with entire layers is more relevant to the present discussion and ties back to layer-level tasks described earlier in section 4.1, task categories D1 and D2. The Donatian system offers 3 different spatial organizations of layers. 1. Small multiples. 2. Stacking the layers on top of each other. And 3. Animation. Starting from the small multiples view, the analyst can drag and drop a layer onto another one to stack them and more easily compare their elements based on the distinctive layer color. In the stacked mode, a set of title bars provides an affordance to reorder the layers in the stack interactively. The title bars also include reconfiguration tools, e.g. choices of layout algorithms that are applied to the layer being manipulated or to the whole stack of layers. Crossing-based interaction across the set of title bars is used to achieve flipbook animation, also for the sake of comparison across layers. This seems quite a natural approach when the layers are defined as consecutive snapshots of a dynamic network. Also, in the stacked mode, Donatian clusters nodes from different layers together based on their spatial proximity in the pixel space. The analyst is able to edit the resulting clusters interactively by pulling a node out, or by dragging and dropping a node on another node or group of nodes to merge them. Merged nodes carry a color-coded pictogram relating them to the layers they occur in. More structured layer organizations may prove to be necessary, e.g. a hierarchy of layers. This ensues from the concepts of aspects, layers, and elementary layers put forth by Kivala et al., but also from many real application needs. From an interaction perspective, merging layers together or splitting them apart becomes a matter of collapsing or expanding their parent node in that layer hierarchy. In this vicinity, the Ontivus system, SMER06, uses an ontology visualization to steer the associated network visualization. An ontology could be seen as an artifact representing the layer structure of a multi-layer network. The onion graph application, SLT*14, provides a hierarchical focus and context approach targeted specifically towards heterogeneous data. The hierarchy provides different levels of abstraction based on node type, role equivalence, and structural equivalence. In their example use case, using an academic publication data set, the heterogeneity of the data is derived from node types, and edges only exist between certain node types. There is no formal layer definition, and the abstraction used to provide the hierarchical focus and context is applied across all data types and does not fully consider the heterogeneity of the data. Such abstractions could be adapted to be applied on a per-layer basis. This could be very useful in multi-layer systems, particularly for comparison of complex layers. For 0.5 attribute visualization. As with standard network data, node and edge entities in multi-layer networks may have many attributes, either categorical or numerical, associated with them. However, within a multi-layer network, attributes of nodes are not only considered within a single network context. For 0.5.1 numerical attributes. Attributes need to be considered across layers, and attribute values, especially for numerical attributes, may change across layers, especially if the attributes are derived from graph metrics, which may be calculated on a per-layer basis. An example of this can be seen in the MuxViz toolkit, DDPA15. Here, the authors use an annular ring visualization approach, which shows the values of metrics across layers, with each ring representing a layer, or in some cases a different centrality for a specific layer. See Figure 16. Task Category D1 or D2. Figure 16. Open in Figure Viewer PowerPoint. A screenshot from MuxViz DDPA15 showing the values for a centrality across layers. Each ring specifies a different layer. This basic approach involves completely separating the attribute visualization from the graph structure. To better relate the relationship between network structure and attributes, the attributes may be integrated into the network visualization itself, referred to as augmented network visualization by DMR16A RM15. Or a linked view brushing approach may be taken, by which the relevant related nodes would be highlighted in a network view when selected in the attribute visualization and vice versa, Task Category B. The standard multivariate visualization of parallel coordinates is also a suitable basic visualization technique. In the case where the graph is multiplex and nodes appear in all layers, the different axes can represent a specific layer attribute. Heat maps may also be adapted for a multi-layer use case. For example, the temporal heat maps of Grottel et al. GHWG14 are made suitable for multilayer attribute visualization by using graph layers instead of time slices for each column. See Figure 17. Figure 17. Open in Figure Viewer PowerPoint. The temporal heat map of GHWG14 showing changes in attribute values over time slices. The approach used for attribute visualization relies heavily on the task the user is performing. For example, a scatter plot matrix is one technique by which attributes may be summarized, possibly even across layers. However, if the user's goal is to understand correlations of attributes across layers, an approach, such as the modified multilayer version, the scatterplot staircase, SB-LOS of VO et al. VMCJ10, may be more efficient in terms of comprehension and space. In this approach, scatter plots of the attributes are ordered pairwise based on correlation and common axis. Attribute visualization can also be combined with interaction within the context of multilayer graph visualization to help better understand the connection between layers. The Det-Angler application RMM15 visualizes the level of entanglement of a selected set of nodes by coloring the selection lasso, an attribute measuring internal cohesion of a group, as opposed to group inertia or entropy. SHA-48, also proposed in BNL14. Attributes should not be considered only at a per-node level. Aggregation is an important feature of GraphTrail, DHRL*12, an application which focuses on exploring multivariate heterogeneous networks. It issues standard network visualization encodings, such as NodeLink and Matrix, in favor of aggregate attribute visualizations using a hybrid approach bar charts combined with arc diagrams. Such an approach is beneficial to the characterization and understanding of layers and their interactions. As described in Section 4.3.5, attribute-based visualization can also be used to summarize the structure of a network and allow for network or layer comparison, as done by ManyNets, FPSG10, as seen in Figure 14. For 0.5.2 categorical attributes. An interesting example of categorical multivariate data in a single layer, which could be extended for multilayer visualization, can be seen in the multivariate graph analysis tool of Pretorius and Van Wyck, PEV-W08. Their approach uses icicle plots to describe the hierarchical, categorical attributes of the source and target of a set of directed edges. The source icicle plot is on the left side of the screen, and the one for the target nodes is on the right, with the edge and their associated data drawn in the middle. Such an approach may be easily adapted to compare categorical labels across layers, task category B, combined with edge bundling, as done by Holton HVW08. With hierarchical edge bundling, it could also be used to examine structural and categorical attribute difference between layers simultaneously. Task categories B and D2. It is also possible to consider categorical attribute data as a network layer in and of itself. For example, in the application Ontovis, SMER06, Shen et al. Use a node ontology graph to query a large heterogeneous social network dataset. The node ontology graph reflects the disparity of the attribute, how well distributed it is across nodes, and its edges display frequency of links between the entities. It acts both as a visualization of aggregated categorical data and a layer by which the data set can be better interacted with and understood. For 0.6 empirical evaluation. Many of the multilayer network visualization papers from the information visualization domain described here are either system papers, e.g., RMM15, KRD*15, or design studies, e.g., GKL*13. Evaluation frequently involves user feedback, GKL*13, DHRL*12, visualization expert review, SLT*14, and usage scenarios, DHRL*12, RMM15. There is a dearth of low-level empirical evaluations specific to multi-layer network visualizations, although this is partially because there are few clearly low-level tasks defined, and there is also a lack of existing techniques to compare them with. For example, a novel interaction like that of Dead Angler, RMM15, cannot be compared directly to any other technique. Therefore, an empirical comparison of user performance at a related low-level task is simply not practical. Within domains external to those related to information visualization, there is less demand for performing a thorough evaluation of systems or techniques, so authors may just demonstrate the techniques with a suitable data set, e.g. CMF *14. The MuxVis application displays layers in a 2D plane in a 3D visualization, aka 2.5D, in one of the many types of visualization it offers. However, as mentioned earlier, no empirical evaluation has ever shown such use of 3D graph visualization to be beneficial, with the exception of when viewed with stereo and/or motion or depth cues, WM08, GPK12. 5 Discussion and Open Challenges. The goal of this report is a review of a large set of tools and techniques to support the increasing demand for the visualization of multi-layer networks. Many of the interesting ideas come from related concepts, such as multivariate and faceted visualization. However, neither of these concepts fully encompasses the multi-layer network model. The existing techniques provide a starting point. However, as a result of the complexity of the systems modeled as multi-layer networks, there are still many novel tasks that need to be addressed. Section 5.1. Possible improvements for modeling layers. Section 5.2. Visualization and interaction gaps that need to be filled. Sections 5.3 to 5.5. And empirical user evaluations to be made. Section 5.6. 5.1 Multilayer Networks Task Taxonomy. Tasks are a motivating force for multilayer network visualization as a topic. There are many existing task taxonomies that cover network visualization as discussed in Section 4.1. Our taxonomy of tasks extends these existing taxonomies. The taxonomy of Lee et al. LPP *06 considers graph comparison as a high-level task not covered by their taxonomy. In the definition of multilayer networks, layers become an integral part of the structure, and as a result, layer-related tasks can no longer be considered abstract or high-level. They are as fundamental part of a graph task taxonomy as nodes and edges. However, these aspects of Lee et al.'s taxonomy can be applied to the graph entities within each layer. 5.2 Data Definition. As mentioned in Section 4.2, many of the approaches, particularly from the information visualization domain, did not explicitly mention that the data were a multi-layer network. An important part of understanding the data is determining what aspects, and hence layers, need to be visualized to support the user's goals as early in the design process as possible. As described in Section 2.1, layers can be considered a characteristic of the multi-layer system as a whole, defined either by a physical reality or the system being modeled. However, there are still multiple ways to determine the set of layers for analysis. 5.2.1 Modeling of real-world concepts from the data. Real systems often begin with raw data and not a graph. However, in many of the papers, we have reviewed that the systems are presented with fully organized and clean datasets, e.g. KRD *15, SLT *14. Within the application domains, generating a multi-layer data set for analysis is often a significant focus of the work. DUC 17, ZB 16, GB 15, independent of visualization. It is already recognized that creating a general-purpose graph from real data is a challenge, KHP *11, SBB 18, and doing so across multiple layers can be considered even more challenging. Existing approaches, HP 14, SBB 18, consider the problem from a general graph point of view and could be developed further to consider graph aspects and layer definition. 5.2.2 Entities that encode layer definitions. When modeling layers, it is easy to consider a node-type attribute to characterize an aspect and encode data into layers. However, it is worth emphasizing that there are many other options. Multiple aspects can be combined together, e.g. in the biological domain. One aspect could be omics level and another could be species, resulting in layers that describe an omics level for a specific species. Edge types are used in many cases to generate layers, usually in multiplex cases such as RMM15, DUC17. It is worth remembering the advice of Kivala et al. And be creative. 5.2.3 Analytical Generation of Layers. The raw data may not map to the real-world concepts embodied in a system and may require some processing. If layers are not immediately forthcoming, a clustering approach might reveal structure not explicitly encoded in the data. Consider the example of a predator-prey network. A topological clustering may group animals based on geography, even if geography is not explicitly encoded in the data. While the process is analytical, it still results in a layering that reflects the reality of the system being modeled. Projection is another means by which layers can be created. Bipartite systems can be analyzed by projecting on a node type, LMDB08. For example, a bipartite author paper network where researchers are connected to papers that they authored. A projection on the paper node type results in a co-authorship network of researchers, where two researchers are connected if they ever authored a paper. Such an operation may be adapted to a multi-layer user case. Degree of interest DOI. Functions suggest nodes for inclusion based on what the user has already characterized as interesting. This approach has already been used by the refinery application and may also be applied to datasets that are explicitly multi-layer. LMP17. 5.3 Visualization Approaches. As seen in Section 4.3, there are a wide range of existing visualization techniques which can be used for, or adapted to, visualizing multi-layer networks. There are many aspects of multi-layer network visualization that are opportunities for immediate investigation with respect to visualization. Hybrid visualizations, as discussed in Section 4.3.4, are techniques which can be exploited for multi-layer network visualization. Only a small subset of the range of approaches discussed throughout Section 4.3 have been combined and hybridized, meaning that there are many potential options still to be investigated to support multi-layer tasks. The need to address tasks related to cross-layer entity comparison also means that there may be interesting opportunities with respect to edge routing and visualization. The approach used by CMF*14 is not developed much beyond the original edge bundling algorithm of Holton and Van Wyck, while the bundling of BISB16 focuses on edge routing in the case where the nodes and edges of all layers are presented in a single node link diagram. Within this report, we have intentionally avoided focusing on more complex data modeling approaches, such as hypergraphs. However, it is worth noting that in many applications, particularly within biology, datasets are explicitly modeled as hypergraphs, e.g. the system's biology graph notation, SBGN, LNHM*09, that is often used to describe biological pathways. Representing hyperedges in a multi-layer context, particularly if endpoints belong to discrete layers, is an interesting open challenge. Some multi-layer datasets also contain a temporal aspect, e.g. GB15, and there has been much work done in the field of complex systems on the dynamics of multi-layer networks, BBC*14. However, integration between temporal and other aspects for dynamic multi-layer networks may still offer opportunities for novel visualization techniques. 5.4 Interaction Approaches. Multi-layer network-related tasks and exploration may require novel interaction techniques. As described in Section 4.4, DetAngler is one example of an interaction technique to support multi-layer network exploration, task categories A, C, and D. The Donatian application of HD12 supports interaction techniques related to comparison of multiple layers, task category D2 in our taxonomy, and defining layers for comparison, task category C. However, there is still a large design space to be explored for multilayer use cases, particularly interlayer exploration, task category D, and layer creation/manipulation, task category C. 5.5 Attribute Visualization. Attribute visualization is important for understanding the differences in attribute values for the same node in different layers and understand differences at the layer level via aggregation or summarization. However, many existing techniques can be adapted relatively easily to the multilayer case, as seen in section 4.5. The most novel attribute visualization seen in the Dead Angler RMM15 system is related to a multilayer interaction technique that uses a multilayer metric. Many classical network centralities have been adapted for the multilayer network use case, DSRO*13, KB*14. While MuxViz DPA15 does include some visualization of these types of attributes, as shown in Figure 16, there is much opportunity for novel attribute visualization considering multilayer centralities, integrated into network visualizations to support cross-layer comparisons incorporating both attributes and structure, task categories D1 and D2. 5.6 Evaluation. Task taxonomies are widely accepted to be useful for the evaluation process, KK17, and the tasks described in Section 4.1 should support the evaluation of multilayer visualization systems and techniques. As described in Section 4.6, there is a lack of empirical evaluation for multilayer network visualizations. Crowdsourcing offers a lot of promise for information visualization, BLB*17, particularly for evaluation. A recent survey, BMV*18, of evaluation using crowdsourcing in information visualization has shown that while the majority of evaluated tasks are simple, more complex, and synoptic, tasks are possible. Many existing crowdsourcing platforms do not lend themselves to tasks that are highly interactive. However, the development of new platforms driven by academic needs, such as suggested by HJR*17, may simplify evaluating more complex tasks. Crowdsourcing may be useful to address the lack of evaluation for approaches to multilayer network visualizations, but the complexity of the tasks and the data sets, for the moment, makes it challenging. 6. Conclusion and roadmap for future research. With this paper, we have presented a survey showing the state-of-the-art of visualization of multilayer networks within both the domain of visualization and others. We have shown that multilayer network problems are at the intersection of domain and data. There are many existing techniques that address many aspects of multilayer network visualization that may be used in many situations. We have also identified aspects that require further research. We have identified categories of tasks not covered by existing network task taxonomies and have identified immediate opportunities for research on multilayer network visualization. We believe that the visualization of multilayer networks will play an important role in the future of network visualization, and by working closely with the field of complex systems and the application domains, we can uncover and find solutions to many new visualization-related challenges. As the field of complex networks grows, more application domains will take advantage of the ability to better model and handle the complexity inherent in the systems being studied. Bringing the visualization community closer to the application domains communities, as well as the complex systems communities, will result in improved outcomes for all involved. Organizing interdisciplinary workshops and seminars that include representatives from all communities was found to foster innovation in both science and technology. COAS 99. As experts from various backgrounds get together, they will encounter new and interesting challenges and will need novel visualization and visual analytics approaches to address these problems. Such interdisciplinary gatherings need, however, to follow certain guidelines to maximize their benefit and avoid common pitfalls, BDW 15. In our opinion, the roadmap for future research starts by the following. Reframing user needs and data as multi-layer network problems. Kivala et al. Discuss the range of data definitions, heterogeneous, multiplex, etc., that are covered by their framework. Reframing a user's problem with these descriptions may prevent commonalities between problems being obscured by nomenclature, but more importantly, it will give the visualization researchers more exposure to application domain researchers addressing multi-layer network problems. Closer interaction with the application's domain communities. Consolidating and refining multi-layer network tasks with the typology of Munzner and Bremer, BM13. And developing higher-level task descriptions with the domains will allow for a better understanding of both the core elements of problems across domains and the full range of solutions available. Closer interaction with the complex systems community. To better understand the data, closer interaction with the complex systems community will allow for the use of novel analytic approaches. Multilayer analytics have not been fully exploited in support of visualization, and we have only touched on a few key aspects in this survey. There is a vast amount of new multilayer network analytics, which may be part of the answer to the visualization challenges that arise from the application domains. Acknowledgements. This work was partially funded by the French ANR Grant Blizzard ANR 15. C23-0002-01 and the Luxembourgish FNR Grant Blizzard Inter/ANR/14/9909176. References